Hello everyone, my name is Isabel Vu, and today I'll be presenting all the necessary information you'll need before reading the paper Constraint-guided directed Greybox Fuzzing by Gwangmu Lee, Woo-chul Shim, and Byung-young Lee. This work focuses on improving crash reproduction when we already know that a bug exists in a program. Crash reproduction is important because when a vulnerability in code is reported, developers often know where the crash occurs, but they still struggle to reproduce it with a specific input. Without reproducing the crash, debugging and patch validation becomes much more difficult. The paper proposes a technique called Constraint-guided directed Greybox Fuzzing, which combines ideas from coverage-guided fuzzing and directed fuzzing to reproduce crashes faster. Before discussing the paper, let's briefly review what fuzzing is. Fuzzing is an automated software testing technique that generates large numbers of inputs and feeds them into a program in order to discover bugs. Typically, a fuzzer repeatedly performs 3 steps. First, it generates inputs at random. Next, it executes the program with those inputs. And then, finally, it detects the crashes or abnormal behavior. For example, imagine a PDF parser. If we generate malformed PDF files and feed them into the parser, some inputs may cause memory errors or crashes. Because fuzzers can generate millions of inputs automatically, they are extremely effective at finding security vulnerabilities. However, let me ask you a question. If a fuzzer can explore new execution paths, do you think it will eventually find all bugs? Think about that for a moment. In practice, the answer is no, because the number of possible inputs is enormous. Many bugs require very specific program states or input values, which random mutations may never reach. Let's take a moment to understand why fuzzing is such an important tool in software security. Modern software systems are extremely complex and often contain millions of lines of code. Because of this complexity, it's almost impossible for developers to manually test every possible input a program might receive. Fuzzing helps address this problem by automatically generating large numbers of inputs and testing them against a program. By repeatedly mutating inputs and observing the program's behavior, fuzzers can uncover unexpected crashes or security vulnerabilities. In fact, fuzzing has become one of the most effective methods for finding vulnerabilities in real-world systems. Large organizations such as Google, Microsoft, and Mozilla rely heavily on fuzzing for security testing. For example, Google's OSS Fuzz platform continuously fuzzes open source projects and has discovered thousands of bugs. Some examples of vulnerabilities that have been discovered through fuzzing include the Heartbleed bug, which allows an attacker to extract memory contents from the web server. With that, there's also many other browser vulnerabilities that may be found through fuzzers, and there's also image parser bugs, since when handling large amounts of data through images, those would naturally lead to crashes that fuzzers can find. Now that we understand what fuzzing is and how it plays a role in software security, let's also take a moment to discuss some different types of fuzzing, since this will be useful in helping us understand the paper. So there are several different types of categories of fuzzing techniques, and they differ in how much information they use about the program being tested. The first category is black box fuzzing. In black box fuzzing, the fuzzer has no knowledge of the program's internal structure. It simply generates random inputs and observes the output. While this approach is simple and fast, it often struggles to explore deeper program logic. At the opposite end is white box fuzzing. White box fuzzers use detailed program analysis techniques, such as symbolic execution, to reason about program paths and constraints. This allows them to generate very precise inputs, but these techniques are computationally expensive and often do not scale well to large programs. Between these two approaches is Greybox fuzzing, which is the most commonly used approach today, as well as what we'll be discussing in this paper. Greybox fuzzing uses lightweight runtime feedback, such as code coverage information, to guide input generation. This approach provides a good balance between efficiency and guidance. Tools like AFL and libfuzzer are examples of Greybox fuzzers, and both of those are very widely used today. As stated before, the technique proposed in this paper builds on Greybox fuzzing, specifically a variation called directed Greybox fuzzing, which attempts to guide testing towards specific parts of the program. Now that we know these three categories of black box fuzzing, gray box fuzzing, and white box fuzzing, we can talk about two more approaches to fuzzing, which are coverage-guided and directed. These approaches also play a role in the paper's research. First, we'll discuss coverage-guided fuzzing. Coverage-guided fuzzing improves basic fuzzing by adding feedback from the program execution. Instead of keeping every generated input, the fuzzer measures code coverage, which refers to which parts of the program were executed. If an input causes the program to execute a new path that hasn't been seen before, that input is saved and used as the basis for generating more mutations. On the other hand, inputs that do not produce new code coverage are discarded. This strategy helps the fuzzer gradually explore deeper parts of the program. Coverage-guided fuzzers like AFL and libfuzzer are widely used today and have discovered thousands of vulnerabilities in real-world software. However, even coverage-guided fuzzing can still struggle when we want to reproduce a specific crash location. That leads to the idea of directed fuzzing. Directed fuzzing is designed for a different scenario. Instead of simply exploring as many paths as possible, directed fuzzing focuses on reaching specific target locations in the program. These targets might include a known crash site, a vulnerable function, or a patch location in some newly fixed code. For example, if a security report indicates that a crash occurs in a particular function, directed fuzzing attempts to generate inputs that reach that function. It does this by prioritizing inputs that appear to move execution closer to the target location. Directed fuzzing tools like AFL-Go compute distances in the program's control flow graph and use those distances to guide input generation. This approach can significantly speed up crash reproduction. However, the authors of this paper observed that directed fuzzing still has important limitations. Even when we know where a crash occurs, directed fuzzing may still fail to reproduce the bug. The paper identifies two major limitations. One is that the execution order is ignored, and two is when the data conditions are ignored. In other words, reaching a target line of code does not guarantee that the program will crash. Often, the crash only occurs if certain events happen in a specific sequence or if certain input values satisfy particular conditions. Let me ask you another question. What information about a bug might be missing even if we know the crash location? Typically, what's missing is how the program state evolves before reaching that location. We'll jump right into the next few slides and illustrate these two limitations. The first limitation we'll discuss is the execution order. So this involves the order of operations. Consider a common vulnerability in code called a use after free bug. This occurs when a program frees a block of memory and then later attempts to access it again. For this bug to occur, the operations must happen in a specific order. First, you free the pointer, and then next, you try to use the pointer. If the program executes these operations in the opposite order, or otherwise executes them separately, the bug will not happen. Directed fuzzing may successfully reach both lines of code, but it does not necessarily ensure that they occur in the correct sequence. As a result, the crash may never be triggered. This shows that simply reaching a target location in the code is not enough. We must also consider the program execution path leading to that location. The second limitation involves the data conditions in code. So, for example, many crashes occur only when specific input values satisfy certain conditions. So, for example, imagine a program that crashes when, given a block of memory, your index is greater than or equal to the size. The index is greater than or equal to the size. If the buffer size is 10, then the crash only occurs when the index is 10 or greater. However, random mutations may generate values like 1, 3, 5, 7, 8, or 9, and these values reach the code, but they never actually satisfy the crash condition of being 10 or greater. So therefore, the bug is never triggered. Directed fuzzing does not explicitly guide inputs towards those boundary values, which means that many crashes remain difficult to reproduce. So, these past two limitations that we've talked about, the execution order and the data conditions, these two motivate the main idea of the paper. So the key insight of this paper is that many bugs can be described as a sequence of constraints, and each constraint represents a requirement that must be satisfied before the crash can occur. So therefore, you must reach the target location and the required data conditions, which satisfies the two limitations that we just discussed. So for example, say that you have two constraints, each where you must reach a location and satisfy a specific condition. If both constraints are satisfied in the correct order, the crash is reproduced. Let me ask another question. If some inputs satisfy more constraints than the others, which inputs should the fuzzer explore first? Take a second to think about that. The answer is that the fuzzer explores inputs that satisfy more constraints or are closer to satisfying the next constraint. So this is the core idea behind Constraint-guided directed Greybox fuzzing, or CDGF for short. Constraint-guided directed Greybox fuzzing prioritizes inputs based on how close they are to satisfying the sequence of constraints. So each input is treated as a seed, and the seeds are ranked according to two factors. First, how many constraints the input already satisfies, and second, how close the input is to satisfying the next constraint. So for example, input A may satisfy the first constraint, input B may satisfy constraint 1 and is close to satisfying constraint 2. Now finally, input C may reach both constraints and trigger the crash. So therefore, the fuzzing system would prioritize the seed C over B and seed B over A. This allows the fuzzer to focus its efforts on inputs that appear more promising to triggering a crash. So by doing this, constraint-guided directed Greybox fuzzing can guide the fuzzing process much more efficiently towards reproducing the crash. Now that you have a better idea of what constraints are, the next question is how those constraints are generated in practice. So the paper introduces a system called CAFL, which we'll get more into later, but it automatically derives constraints from available program information. One important source of information is crash reports. These crash reports often include stack traces that identify where the program failed. These stack traces help identify the target location in the program. Another useful source is patch analysis. When developers release a security patch, the modified code often indicates where the vulnerability existed. By analyzing these changes, the system can infer likely conditions that must be satisfied to trigger the bug. The system also uses static analysis of the program's control flow graph. By analyzing the structure of the program, the system identifies possible execution paths that led to the crash location. These intermediate program points become constraints that guide the fuzzing process. Remember that constraints are made up of a target location and the conditions, and these are in the points that we just talked about. For example, if a crash occurs in a particular function, the system might identify earlier functions that must execute before reaching that point. These functions become part of the constraint sequence. Once the constraints are generated, they're used by the fuzzing engine to guide input generation towards satisfying those constraints in order. So now that you know a bit more about how constraints are generated, this will play a huge part in how the experiment sets up the fuzzing system, which now we can talk about. In this research paper, the authors implemented their approach in CAFL, which is a prototype system of constraint-guided directed Greybox fuzzing based on the American Fuzzy Lop fuzzer. So CAFL consists of three main components. First is the compiler instrumentation. This is where the program is instrumented at compile time so that the runtime system can monitor when constraints are satisfied. Next is the runtime checking. So during execution, CAFL tracks whether constraints are met and records information about the program's behavior. And then third is seed scoring and prioritization. So based on the collected information, the fuzzer assigns scores to inputs depending on how close they are to satisfying the constraint sequence. And then with this, the scoring mechanism determines which inputs will be mutated and explored next. This architecture allows CAFL to integrate constraint reasoning into a Greybox fuzzing framework. To evaluate their approach, the authors conducted experiments comparing CAFL with an existing directed fuzzing tool called AFL Go. The goal of these experiments was to determine whether constraint-guided fuzzing could reproduce crashes more efficiently than traditional directed fuzzing. The evaluation was performed using several real-world software programs, each containing known vulnerabilities. These programs included open-source applications commonly used as benchmarks in fuzzing research. The authors measured two main metrics. The first metric was the time to reproduce the crash, which measures how long it takes for the fuzzer to generate an input that triggers the vulnerability. The second metric was the success rate, which measures how often the fuzzer successfully reproduces the crash during repeated runs. By comparing these metrics across multiple programs, the authors were able to determine whether their approach improved crash reproduction performance. So, what were the results of this experiment? Well, I won't spoil too much. If you'd like more information on the second metric of success rate, or how often the fuzzer successfully reproduced the crash during repeated runs, you can read the paper for yourself. But for now, I'll focus on the metric of how much time it took to reproduce a crash. Turns out that CAFL reproduced crashes approximately 2.88 times faster than AFL Go, which shows that CAFL more effectively prioritizes inputs that satisfy the necessary constraints. As stated before, the experiments were conducted on several real-world programs, which demonstrates that the approach can improve directed fuzzing in practical scenarios. However, like most research work, this approach also has its limitations. First, the system requires crash information or code patches to generate the constraints. This means that it may not be entirely useful when no information about the bug is available. Second is that the constraint inference may be inaccurate, which can misguide the fuzzing process. Third, the additional instrumentation introduces some runtime overhead. And finally, the evaluation focuses mostly on memory-related bugs, which means the approach may not generalize to all vulnerability types. So, for example, logical vulnerabilities or complex multi-step exploits may be harder to model using simple constraint sequences. So let me ask you a question. What other kinds of bugs may still be difficult for this technique to detect? Now that we've learned about constraint-guided directed graybox fuzzing, we've seen the experiment, and we've seen the results of that experiment. Let's summarize all that we've learned today. So first, coverage-guided fuzzing and directed fuzzing both improve traditional fuzzing by focusing on specific target locations. However, it ignores two important factors, which are the execution order and the data conditions. So this paper introduces us to constraint-guided fuzzing, which models bugs as sequences of constraints that must be satisfied before successfully reproducing a crash. So by prioritizing inputs that satisfy more constraints, the approach significantly improves crash reproduction speed. So to close out this discussion and before you can really start to dive into this paper, here are a few more discussion questions. Could constraint-guided fuzzing be applied to other types of testing? What challenges might arise when generating constraints automatically? And how might machine learning improve fuzzing techniques in the future? These questions highlight how fuzzing research continues to evolve and how techniques like constraint guidance could be combined with other approaches. That's all for today. Thank you so much for listening.